Good morning. Good morning to all. I'm Dr. Ganesh, Assistant Professor, Department of Aeronautical Engineering, Hindustan College of Engineering and Technology. In this video, I'm going to discuss about energy method. Strain energy. So, in energy method, we are using strain energy to find the deflection of the different structures. So, what is strain energy? When your body is subjected to gradual, sudden, or impact load, the body deforms and work is done upon it. If the elastic limit is not exceeded, this work is stored in the body. This work done or energy stored in the body is called strain energy. Energy is stored in the body during the deformation process, and this energy is called as strain energy, where strain energy is equal to work done on a structure. Resilience. Total strain energy stored in a body is called as resilience, where U is equal to sigma square divided by 2E into P, where sigma is stress and V is the volume of the body, and U is the strain energy stored in a body. And proof resilience. Maximum strain energy which can be stored in a body is called proof resilience. U suffix P is equal to sigma E square divided by 2E into B, where sigma E is the stress at elastic limit. Modulus of resilience. Maximum strain energy which can be stored in a body per unit volume at elastic limit is called modulus of resilience, where U suffix m is equal to sigma E square divided by 2E. Generally, strain energy in a structure can be stored due to various types of loads. First one is axial load, and second one is shear load, and third one is due to torsion, and fourth one is bending. So all the different loads acts on a structure. The strain energy will be produced stored in a structure. First we consider the strain energy due to axial load or gradual loading. Consider a bar of length L placed vertically, and one end of it is attached at the ceiling. Let T is the gradually applied load, and L is the length of the bar, and A cross-sectional area of the bar. Del L is the deflection produced in the bar. Sigma is the axial stress induced in the bar, and it may be a tensile or compressive stress depending upon if the bar under consideration is under tensile or compressive. And E is the modulus of elasticity of the bar material. If we draw a graph between load and the deformation, if the load increases gradually, the deformation is also increases gradually up to the elastic limit. So the curve, the area below this curve, that gives the work done on the structure. Work done on the structure. And similarly, if you draw the graph between resistance and deformation, the same curve you will get an inclined curve up to the elastic limit. So the area below this curve is the work done on structure. So work done on the bar is equal to area of the load minus deformation diagram, and that gives off into P into del L. So work stored in the bar is equal to area of the resistance minus deformation, that is 1 minus 1 by 2, 1 by 2 into R into del L, where 1 by 2 into R can be written as sigma into A into del L. Now work done is equal to work stored. So we can get 1 by 2 P into del L is equal to 1 by 2 sigma into A del L. By cancelling 1 by 2 1 by 2 and del L, you can get P is equal to sigma A. This is the stress due to gradual, and strain energy can be given as half into R into del L, that is equal to half into sigma into A into del L. And if you are replacing del L is in terms of strain, half into sigma into A into epsilon into L. That epsilon can be written as sigma by E, and we can have half into sigma into A into sigma by E into L. So finally we got strain energy is equal to sigma square by 2E into A into L. So A into L is called as volume of the body. So your strain energy U is equal to sigma square divided by 2E into volume. So next is strain energy due to shear load. If tau T is the uniform shear stress produced on the material by external forces applied within the elastic limit, the energy stored due to shear loading given by U is equal to tau square divided by 2G into D, where tau is the shear stress and G is the modulus of rigidity. Consider a square block ABCD of length L. Faces BC and AD are subjected to shear stress tau. Let the face AD is fixed. The section ABCD will deform to AB1C1D through the angle phi, where phi is the shear strain. So tan phi is equal to B into B1 divided by L. So phi is very small, so tan phi is equal to phi. So phi can be written as B into B1 divided by L. So this is called as shear strain. So for force P on face BC is given by P is equal to tau into BC into L. When P is applied gradually, so gradual load U is equal to P by 2 into B into B1. So U is equal to half into tau into BC into L is equal to BB1. So BB1 can be written as phi into L. So we can have U is equal to tau square divided by 2G into volume. So the elastic energy stored due to shear loading is known as shear resistance. The strain energy due to torsion. If you are applying a torsion or twisting moment on a shaft, the strain energy will produce. So we have seen that when a member is subjected to a uniform shear stress tau, the strain energy stored in the member is tau square divided by 2G into P. Consider a small elemental ring of thickness dr at radius r. So UR is equal to tau square r divided by 2G into volume. So UR is equal to r divided by small r divided by capital R into tau that whole square divided by 2G into volume. So by rearranging this equation, we can get r square tau square divided by capital R square 2G into volume. So by cancelling and by substituting the volume, we have UR is equal to tau square R cube divided by R square G pi L into dr. The total strain energy for the whole section is obtained by integrating over a range from R, small r is equal to 0 to small r is equal to capital D by 2 for a solid shaft. So if you are substituting U is equal to integrating of 0 to capital D by 2 tau square R cube by R square by G pi L dr. So by integrating this, finally we got tau square pi L divided by R square G D by 2 the whole power 4 by 4. So where U is equal to tau square pi L divided by R square G into D power 4 by 64, and that's equal to tau square by D square by 4 into pi L by G to D power 4 by 64. So by cancelling, by substituting R is equal to capital D by 2, we have U is equal to tau square divided by 4G into volume. The strain energy due to torsion. The next strain energy due to bending. Consider two transverse sections 1 to 1 and 2 to 2 of a beam distance dx apart as shown in figure. Consider a small strip of area dA at distance y from the neutral axis. A bending moment in small portion dx will be constant, and m by I is equal to sigma by y, as sigma is equal to m by I into y. The strain energy stored in small strip of area dA, so U is equal to sigma square by 2E into volume, where U is equal to 1 by 2E is equal to m square y square divided by I square into dA into dx. And strain energy stored in the entire section of the beam is to be getting by integrating the equation number 2. So your total strain energy U total is equal to summation of y is equal to yt to y is equal to yc. So 1 by 2e into m square y square divided by I square dA into dx. So by considering that summation of y square into dA can be written as second moment of area. So by total strain energy can be written as m square by 2EI into dx. Now for strain energy in the entire beam, integrate between limit 0 to L. So your strain energy U is equal to integration of 0 to L m square by 2EI into dx. So this is the strain energy due to bending. Thank you. Thank you for watching this video. Thank you.